Hello everyone, I'm Ilshade Ilyas and I'm from VIT University, Vellore. I'm taking a Computer Organization in Architecture course under the guidance of Dr. Danaval. My registration number is 18BEC2028 and my serial number is 62 in A2 slot. So I'm going to answer questions from digital assignment 2. So the questions are based on a journal and I have chosen my own journal, which is having the title Floating Point Division and Square Root, choosing the right implementation. So I'm going to answer based on this journal. So the first question is explain how the selected paper relates to the COA syllabus or curriculum. So the journal emphasizes on fixed point arithmetic due to expected power and area saving over floating point computation. Also, it relates to the COA syllabus mostly on Module 2, which consists of the topics of arithmetic and logic unit, signed addition and subtraction, multiplier architecture, signed and unsigned multiplication, both multiplier, array multipliers, restoring and non-restoring division. So on this module, it relates to the COA syllabus. And also the paper investigates the effects of a simplified floating point arithmetic applied to the FMA-based floating point unit in the associated software division and square root operations. So coming to the second question, it says to draw the existing architectures discussed in the paper using an EPS file format. So the independent add multiply configurations are as shown here. It has a register file and a multiply and add, and it also consists of a max shown in a pink color. So the addition operation has a latency of 2, whereas the multiplication has a as well as the multiplication has a latency of 2, and throughout both addition and multiplication has a value of 1. In multiply accumulate configuration, it has a register file in multiply in which the multiply goes back to the register file, and it has a latency of 2 and throughout of 1 value. So the FPO topology with subtractive divide or square root functional unit and independent add multiply consists of this things like register file, multiply, add, divide, square root, and max. Here is the FPO topology with subtractive divide or square root functional unit and multiply accumulate configuration. And this one consists of a register file, multiply accumulate, and divide or square root with max. Okay, now the next question is to draw the tabulated results and graphs in the EPS file format. So I have drawn the results. Here it's shown here. It has the values for the divide fast, divide slow 1, divide slow 2, square root, and divide fast, divide slow 1, divide slow, and divide for the square root for different values. Here also it says the it shows the cycle time in nanosecond, the latency cycles for addition and subtraction and multiplication, square root, and divide. So the improvement in execution time percentage of the given rotation benchmark by implementation for the independent configuration is given in this table. So for 8-bit seed Goldsmith, the maximum is 0 and the minimum is 0, and average obviously will be 0. And in a 16-bit seed Goldsmith, the maximum is 9.9, whereas the minimum is 1.6 and the average is 5. And radix for SRT has a maximum of 20.9 and minimum of 7.2 with an average of 15.2, and the radix 16 SRT has a maximum of 46 and 7.2 minimum with a 23.4 of average. So divide or square root performance of multiply accumulate implementations are given here with the latency divide and square root values. Also here for divide or square root performance of independent implementations of the algorithms with the latency value is given. For multiply accumulate implementations also, the table has given the values. So here it shows the relative cost of different divide square root implementations. Also it gives the area factor for the 8-bit seed multiplicative. It has an area factor of 1. In a 16-bit seed multiplicative, it has an area factor of 22, and 1.5 for the radix 4 SRT and 2.2 for the radix 16 SRT. So the next question is to draw the proposed architectures discussed in the paper. So there is a register file, there is a multiply, add, divide in square root, and there are 8 maxes, 2 for each multiply, add, divide, and the 2 are common for all the 3. Coming here, this is for the dual issue independent add multiply configurations with other coupled unit. This one has only 1 max, and the multiply doesn't have any maxes here. This one is for independent add multiply configurations, multiplier, couple, divide, square root unit. And this one, on this case, this one the multiplier didn't have a max, and this one the add don't have a max. Okay, the fifth question is to draw the transistor level internal diagrams using electronic schematic capture in simulation tools in EPS file format. So there is a residual carry register and residual sum register. There is result digit selection, carry save adder, on the fly conversion and factor generation here. The block diagram is clearly shown here. Okay. Next is to compare the proposed architecture with existing architecture in our reference books. So here the simulations in the previous section assumed an issue rate of 1 floating point instruction per machine cycle. So this situation holds in such processors as the Power PC series, where the floating point unit is a single pipeline, in the Intel P6, where the arithmetic functional units share a single set of inputs and outputs. However, many recent machines, including the MIPS 10000 and Sun Ultra Sparks, can generate up to 2 floating point instructions at once. So we have also performed a set of simulations to determine how dual instruction issue affects the performance balance between multiplicative and subtractive methods. So as shown, the multiple instruction issue strengthens the performance advantage of subtractive implementations. This is what one would expect given the increased parallelism of operations afforded by the separate functional unit for divide or square root operations. So this data support the claim that subtractive methods are better suited to superscalar implementations. So coming to the next question is to list the advantages of the proposed design over the existing design. So I have listed out 3 main advantages. The first one is the software operations are proposed with attain near exact precision, with twice the performance of exact algorithms, and resolve overflow related errors with inexpensive exponent manipulation special instructions. And the second one is it requires only 5 multiply add operations to achieve reasonable results, while an exact algorithm using an IEEE compliant FPU requires 11. So there is 6 reduced multiply add operations. So for example, if only 10% of arithmetic operations required by an application were divisions, this would reduce the final instruction count by more than 1/4. Okay, so the third advantage is software operations are proposed which attain near exact precision with twice the performance of exact algorithms, and they resolve overflow related errors with inexpensive exponent manipulation special instructions. Okay, the next question is list the merits and demerits of the proposed and existing techniques or hardware. So the merits include it does not require much more hardware to implement than a multiplier, and the ability to execute all arithmetic instructions in a single compact unit. Addition may be emulated simply by multiplying by 1 and multiplication by adding 0. And the final measure, the fused property of the FMA could be dropped, which reduces it to a plain multiply adder. Coming to the demerits, the main disadvantage of this scheme is the need to store the scaling factor, increasing pressure on the registered file, and some FMA architectures are difficult to reconcile with. So these are the demerits. Okay, so coming to the application of the proposed design. Uh, the proposed design has an applications in efficient software-based implementations of division and square root. It can also be engaged in a replace separate hardware units for these operations. Okay. The last question is to draw the flowchart or algorithm or transistor level circuit proposed in the design. So I have given the algorithm for the divide fast, divide slow, and square root from the proposed architecture. So the algorithm for the divide fast is first the data is given as a single precision float dividend A and divider B. So the result will be the quotient of A by B. So we begin by initializing divisions A, comma B by A bar, B bar, and C bar. Then the reciprocal approximation of B is given as Y. Then Q naught will be set as A dash, and at last it will be multiplied by power of 2, giving Q2 as a return. And for the divide slow also, the algorithm is given here. Okay, square root algorithm at last is here. So the data given is a single precision float A, and the result will be the square root of A. So we begin by initializing square root of B in B, and then inverse square root approximation of B, which is noted as Y naught, and we return G2 dash, which is multiplied by power of 2 as a result for the square root. This was all. Thank you.